The first example is the dynamics of the free particle. Here the Hamiltonian is just the kinetic energy. To sharpen our expectations, we again first make reference to the classical case. There we would say that the particle does not experience any forces, so that along with its energy, momentum is also conserved, but the particle can certainly move around. That's well hidden in the most natural stationary solutions of the quantum system, because these are our familiar momentum eigenstates, of the form of plane waves that are extended over all space. By accounting for the explicit expression of the associated energy, we can elevate these to time-dependent solutions. And even when we combine two such states with the same energy, as we would do when we construct the most general stationary solutions, there is no time dependence in the probabilities or the expectation values, simply because the time-dependent factor again drops out from all calculations of these quantities. All that we see is that the probability density in space is no longer uniform. Well, these restricted superpositions are also still not normalizable, and hence what we really would like to do is to start with a solution where the particle is a bit better localized, and then see what happens in the subsequent dynamics. This is indeed what we will be aiming at, but first we set up the general time-dependent solution by exploiting the general features of the problem, so avoiding tedious calculations for a little while. Without loss of generality, we set the initial time to 0 and write the most general solution as a sum over all the stationary solutions. This is now really an integral, and it is easiest to have it over p and not e, so that we only have one solution at any value of the parameter that we integrate over. The coefficients in front we now call psi tilde of p. We see that this is consistent with our earlier notations when we look at the initial conditions. There the wave function is simply written as an integral over plane waves, just in the way that we encountered it when we introduced the momentum wave function. So psi tilde of p is just that momentum wave function, and hence we obtain it from a Fourier transform of the position wave function at that initial time. What we have written here is indeed completely equivalent to what we did in our construction based on the superposition principle, but reformulated in terms of an integral over momentum, which helps us to directly connect to our earlier calculations. Now, when we let this state evolve over time, the only thing that changes is the coefficient in front of the plane waves, which is just our familiar time-dependent exponential factor. And so when we work out the Fourier transformation with this state at a different time, then this is just multiplied by this exponential factor. That's then also the momentum wave function at that different time, and when we take this to obtain the momentum probability density, this factor drops out. So, as somewhat anticipated, the momentum probability is stationary. This is as far as we can go for momentum on such general grounds. Next, we have a look at position, and for this we consider a more concrete expression for the initial conditions, just so that we retain a chance to interpret our results in physical terms. For this, we consider the case that our initial state is a so-called minimum uncertainty wave packet. This is a state in which position and momentum are relatively well defined, to the extent that the uncertainties fulfill the uncertainty relation as an equality. An example of this would be the ground state of a harmonic oscillator, where the uncertainties depend on the mass and the angular frequency. But we can simply take a function of the same general form, as the initial state is not further constrained in any way. Indeed, we generalize this expression slightly by including a plane wave component, with this parameter p naught here, which corresponds to a finite expectation value of the initial momentum. In the Fourier transform, this term immediately gives rise to a shift of the momentum p, so that we can use our earlier results from the harmonic oscillator to write down the corresponding momentum wave function. This is now symmetric about the value p0, verifying that the expectation value of momentum is indeed p0, but besides this it does not change the shape of the function, which remains a Gaussian. And this also means that the uncertainty in momentum is unchanged, so that we do not need to carry out any further calculations to determine it. In principle, we could have also added an initial shift in position, but this will not be relevant for our main point. So the state given here simply has uncertainties delta x equals to sigma and delta p equals to h bar divided by 2 sigma, along with a vanishing expectation value for position and a finite expectation value for momentum. And this is our initial state, where our question is how all of this changes over time and in particular in regard to position. Well, we can find the time-dependent position wave function by inserting the momentum wave function in our expression using the plane waves, and then evaluating this integral at a given time t. Note that this integral is still of the form of a Gaussian integral, as p only appears in the exponent and only at most quadratically. This means that even though this integral is perhaps a bit more tedious with its mix of real and imaginary terms, it can still be carried out exactly along the same lines as we have done before. I therefore just state the result. It is quite lengthy, so let me mention that there is certainly no need to try and memorize it. So let us have a closer look at this. The last term is just an exponential factor with a purely imaginary exponent, so when we take the absolute value square of this, we just get 1. That's useful because taking the absolute value squared gives us the position probability density. So this takes a somewhat simpler form given here, which indeed still just looks like a Gaussian. But there are 2 modifications in here from our original expression, with the most obvious one being the shift of the center of the wave packet. This translates into an expectation value of position given by p0 t divided by m. And so this just moves with the classical velocity of the free particle as determined by its average momentum p0. So for the first time in this course, we meet an observable physical quantity that indeed changes over time. This second, more subtle modification is encoded in this expression sigma t here. This expression appears in place of the initial uncertainty and indeed changes over time too. As a matter of fact, it increases, first slowly, but after a certain time linearly. Now we found above that the uncertainty momentum does not change, and so the product of the uncertainties also increases over time. So apart from the time of the initial condition, the wave function is no longer a minimal uncertainty wave packet, but spread out by a larger amount. Indeed, the lengthy expression of the wave function above has a different form than even the most general minimal uncertainty wave packets that we can write down. This effect is known as dispersion and is a very general wave effect, so let me briefly point out this wider context. Dispersion arises whenever a wave is made out of different components that travel with a different velocity, as here is indeed the case. We see this most explicitly when we reformulate the energy-momentum relation in terms of frequency and wave number using the Planck and the de Broglie rules. From this we can work out the standard group velocity, which indeed depends on the wave number. As a matter of fact, this group velocity just corresponds to the velocity of the particle when we again apply the de Broglie rule. Indeed, when we look at the rate by which the position uncertainty increases for large times, we can see that this can be interpreted as arising from the spread of the velocities. Just for information, let me remark that these considerations can be put onto a firm footing by making use of methods of asymptotic expansions, in particular the methods of stationary phase and steepest descent. and can then be applied to more general initial conditions. For instance, with such advanced methods, one finds that quite generally for large times the position probability approaches a scaled version of the initial momentum probability as given here. This is exploited in indirect measurements of the momentum in so-called time-of-flight experiments, and these are, for instance, a standard tool for experiments on cold atomic gases. However, the insights that we obtained from the described concrete example already reveal the main qualitative features, and hence this suffices for our purposes. Let us instead turn to our second example. Our second example concerns the harmonic oscillator, so the system with this familiar Hamiltonian, including this parabolic potential here. The ground state is a Gaussian function of now a very specific width, and this corresponds to a state of energy E equal to h bar omega divided by 2. For our initial condition, we will also utilize such a Gaussian function of the same width, but we will allow it to be displaced away from the equilibrium position at x equals to 0. So this can be simply written in the form given here, where for clarity I now use a capital X for quantities related to this additional displacement. Capital X naught is then also the initial expectation value for position, while the initial expectation value for momentum still vanishes, and the uncertainties in position and momentum remain as before. To shape our expectations, as always, let us first consider the classical case. Classically, when we displace the oscillator by a certain amount in position and then let it move, it will oscillate with the angular frequency omega, and this frequency is independent of this displacement. So compared to the free particle, the classical motion is much more systematic, and indeed we will find that this feature is replicated to a very large degree also in the quantum problem. As always, the quantum mechanical version of the harmonic oscillator can be tackled by various methods. Here we will focus on the most explicit construction, where we start from a trial solution with some free coefficients. And then we see whether we can find the solution by adjusting these coefficients. We could also expand our initial condition in terms of the stationary states, but we have already seen how this works in the previous example. Furthermore, we could also employ the algebraic approach, and this is indeed very efficient. But we will reserve this for later and return to this in the next chapter, where this will be useful to illustrate the general operator-based methods developed there. So we start from a suitably simple trial function, which codifies our hope that we can capture the motion based on a time-dependent displacement capital X of t, up to some phase factors that drop out of the probability density in position. In these phase factors, we have another function capital P of t, which really enters as in a plane wave with a time-dependent momentum, and an extra factor S of t, which is just a pure phase factor, assuming that all of these functions are real. So our main ingredient in here is the displaced ground state wave function, and we try to make this work in particular with an uncertainty that does not depend on time. Our next step is the same as always when equipped with such a trial wave function. We introduce it into the Schrödinger equation, now the time-dependent one, and work out all the required derivatives, including now also with respect to time. From this we will identify conditions so that both sides of this equation are identical, which we now not only require for all positions, but also for all times. We may well find that these conditions cannot be satisfied, but here we will see that everything works out. First, the derivatives can all be worked out by using the chain and the product rules. This results in these expressions here. In here we denote temporal derivatives by a dot and spatial derivatives by a prime. The last factor in these expressions is common to all terms and therefore cancels when we insert this into the Schrödinger equation. Here we can also use that including the displaced argument, psi0 satisfies the Schrödinger equation with the correspondingly displaced potential. This leaves us with terms of a clearly identifiable structure. For instance, they are linear or constant in position and proportional to psi0 or psi0 prime. And in these there are also clearly identifiable real and imaginary parts, and as all remaining quantities are real, we can read off a number of conditions. The first two conditions only involve capital X and capital P. And this gives us two coupled differential equations that are simply identical to the classical equations of motion of the harmonic oscillator. So the general solutions are given by sine and cosine functions, and with our initial conditions they are then fixed as stated here. From the remaining terms we first find a condition for the derivative of S. And then using our equations of motion for capital X and P, we can rewrite this so that this can be directly integrated. Here we drop any additional integration constant, as this is just contributing an additional overall phase factor to the wave function, which again drops out of all physical quantities. Just for information, let me mention that this quantity S of t has also a classical interpretation. It corresponds to the so-called action of the system, which is a central notion in advanced versions of classical mechanics. So we indeed have satisfied all conditions, which verifies that our initial trial solution is consistent. And when we insert here our specific expressions for capital X, P and S, we obtain our final result, the time-dependent solution of the harmonic oscillator with the initial conditions given by a spatially displaced ground state wave function. I'll write it out here completely, but just to give you an idea how this then looks concretely. We conclude that in many respects this solution replicates the classical motion. This applies in particular to the expectation values of position and momentum, which are given by the functions capital X of t and capital P of t, and hence follow the classical motion. The position and momentum uncertainties are independent of time and hence remain at their values where they fulfill the uncertainty relation as an equality. So also in this respect, one can say that the solution is as classical as it can be. But given that these uncertainties are of course still finite, the quantum system also displays some differences, and one we can read off straight away when we look at the expectation value of the energy. For this we return to the expression where we calculated the action of the Hamiltonian on the trial wave function. The expectation value is given by the scalar product of this with the wave function itself, which we can evaluate straight away. I give you the result here. From this we find that this is given by the expression of the classical energy plus h bar omega divided by 2, hence plus the ground state energy of the oscillator. We can also work out the energy uncertainty, and this is again finite as stated here. As mentioned above, we will return to this problem when we have developed some even more general and powerful methods in the next chapter. These will allow us to understand and replicate the behavior of these expectation values in a very direct way.